Hello AP Statistics students. In this video, we're going to take a look at how to make a confidence interval for the slope of a population regression line. All right, so when we take a sample of something for two variables, we can find a regression line if there's a linear association. But that's just one possible regression line. And so the slope is only one possible slope. If we took another sample, we'd get something a little bit different. So what is the confidence interval of where the true slope could be based off of our sample? So usually, yes, there's the entire four-step process for this, right? But we're not going to do the whole thing quite yet. The conditions are new, and so we're going to leave those for later. Right now, we're just going to focus on the process, how to actually make the confidence interval. So let's take a look at this. First, let's remember how to actually make a confidence interval, okay? So if you remember a confidence interval, the basic structure here is you take your point estimator and then we add and subtract the distance we have to go out to capture the true proportion or the true parameter blank % of the time, whatever power our confidence interval has. So the way we do that and figure out what our margin of error is, right? This is the margin of error. It is a critical value times the standard error. The estimate for the standard deviation of the variable you are looking at. So if you remember for the critical value, sometimes this is going to be a z star, sometimes it is a t star. For the how many standard errors do you have to go out to capture the parameter as many times as you need to? So if you remember, z star was all about proportions. And so we would use inverse norm. You're actually allowed to use the normal model there. But it didn't quite work for means, right? It didn't capture the true, in this case, mean enough times to make our confidence level. That's why we had to use the t-distribution instead. And so to find the t star, you would use an inverse t. This is also the one we are going to use for slopes. All right, so also for slopes. We also have to use the t star. I don't want to get into why. The book glosses over it pretty quickly, so I don't think it's super important for us to really know the inner workings of why it's a t star instead of a z star. But this is, again, the general structure of the confidence interval. So let's use it. This problem might look familiar. The book has recycled it a couple of times. Everyone knows that cars and trucks lose value the more they are driven. Can we predict the price of a used Ford F-150? The F-150 is, I think, the most selling car in the United States, actually. I know it's the highest selling truck, but I think it might be overall, possibly as well. A Ford F-150 Super Crew 4x4, if we know how many miles it has on the odometer. A random sample of 16 used Ford F-150s was selected among those listed for sale on autotrader.com. The number of miles driven at and price were recorded for each of the trucks. Here are the data. So we've got ourselves quantitative variables. We can definitely make a scatter plot of all this, right? And what we want to construct and interpret a 90% confidence interval for the slope of the population regression line. what would the slope actually be? So we've got some information here. They give us the scatter plot and they give us a computer printout of the linear regression information for this sample. So the things that we have done, remember the linear regression equation a plus bx that we used for so long? So if we were to take our linear regression printout and write this linear regression line, it would be price is equal to, our y-intercept is right here, the constant coefficient, 38,257, plus the slope is right here. This is going to be our point estimator when we do our confidence interval. That's the slope of the regression line. So I guess I should put minus then, shouldn't I? Minus 0.16292 times miles. How many miles has it been driven? Again, you don't need to use y and x. It's almost sometimes easier just to put the words in the formula. Kind of nice that way. So now we want to create a confidence interval, though, for this slope. That really describes the relationship here, right? For every 1 mile driven, for every 1 extra mile driven, we expect the price to go down by 16 cents. 0.16292, but basically 16 cents, right? For every 1 mile driven, we expect the price to go down 16 cents. Think about that as you drive around in your car, possibly. Every mile, 16 cents. Depreciation, it hurts sometimes. So we're going to create that confidence interval. So we get our point estimator, 0.16292 plus or, oh, it's plus or minus. Did I forget the minus before? I think I did, because you add and subtract, right? Let me go back and fix that. Oh, I did put the plus and minus. Look at that. All right. I'm just imagining things. Good. 0.16292 plus or minus. So first thing we need is the t star. How many standard errors are we going to have to go out to get our 90% confidence interval? So I'm going to do that over here for my t star. So if you remember the t star, it looks pretty normal. But I want a 90% confidence interval. So I know the area is 90%. I need these boundaries, which is why this is an inverse t, right? So inverse t. Where is my calculator? I've got the Casio right now, so let me do that. So no matter which calculator you have, though, you need to find the inverse t function. Okay, second distribution on the 84. So what area do I need here? Well, if it's 90% in the middle, it's 5% on this tail, 5% on that tail, and the inverse functions are always always the area to the left, right? So if I want this boundary, the thing I have to type in is 5% here. 5%. Ooh, degrees of freedom. How many degrees of freedom? Let's write that down. So the degrees of freedom in this case, n minus 2. What? Yes, n minus 2 this time. N minus 2. Again, the book says, yeah, I'd rather not touch on this subject of why it's n minus 2. It says it's beyond the scope of this course. For me, in my mind, I justify it as n minus 2 because we have an x and a y. Because we have 2 different variables there, that's how I remember it's n minus 2. So in this case, our degrees of freedom will be, let's see, they had 18, right? Was our sample size? Oh, 16. We had 16. So our degrees of freedom are 16 minus 2. So our degrees of freedom will be 14. So our T star will be 1.76. All right, 1.76. Maybe throw some more decimals in there, huh? 1.3. That's how many standard errors, all right, standard deviations essentially, we have to go out to capture the true slope 90% of the time. What is that standard error, though? What is the standard deviation of the slope? There's an equation, all right? There's an equation. I'd rather not, because most of the time, I think all the time, either your calculator will give it to you or they will give it to you right here. Here is the standard error of the slope, which is right here. Okay, I talked to their stats teacher, and he's like, yeah, no, that these types of problems, A, they're rare, super rare. B, they give you the computer data like this. Okay, so I don't think you need to come up with the standard error. The book says, yeah, you don't really calculate this by hand. So there it is. The standard error is 0.03096. It is the standard deviation, essentially, of the slope, or at least our estimate of it using the sample. So there is our confidence interval. Of course, we can plug this into the calculator, right, to actually find the interval if we want it, right? Let's do that. So menu, home. So 0.16292 plus 1.7613 times 0.03096. That's the plus, right? That's the bigger one. So 0.2174. And then 0.16292 minus 1.7613 times 0.0309. 0.1084. All right, so there is our confidence interval for the slope of this regression line. So we are 90% confident the slope of the population regression line for context time, right? Can I remember what the context was? Did we have a year? Used Ford F-150s for the price of used Ford F-150s based off their mileage. All right, we want to make sure we include both variables here, right? We're looking at the regression line for price based off of mileage, my X and my Y. All right, we are 90% confident the slope of that regression line is in the interval 0.1084 to 0.2174. That sentence is pretty much the same as always, right? A little bit different with the context because we have to say, hey, it's the population regression line. And then don't forget, it's to describe both variables, the price of the Ford F-150 based off of their mileage, okay? But otherwise, that sentence should sound very, very familiar. to you. All right, let's do one more there, shall we? To really feel like we got that process, to practice it, but hopefully the process not too bad, right? All right, many people believe that students learn better if they sit closer to the front of the classroom. Does sitting closer cause higher achievement, or do better students simply choose to sit in the front? To investigate, a statistics teacher randomly assigned students to seat locations in the classroom for a particular chapter and recorded the test score for each student at the end of the chapter. This sounds like an experiment without consent, doesn't it? You're not allowed to give treatments to people without them being volunteer. Maybe they signed something at the beginning. I don't know. But just teachers put people towards the front or back or in place for very specific reasons sometimes, and just to do it randomly is actually kind of bad. So here are the data, along with output from a regression analysis. Construct and interpret a 95% confidence interval for the slope of the true regression line. All right, so we take all of that. Here is the scatter plot. It looks, not a very great R value there, I'm guessing, but it is somewhat negative in its correlation there. So let's create a confidence interval for this point estimate right there. That's our slope, right? So our slope is 0.947. I'll write the whole. So our regression equation would be the test score is equal to, it's not that one. That's the standard error, isn't it? 85.71 plus negative 1.117 times row number. So a slightly negative association there, huh? But we know negative 1.177 will have some sample variability. So what is the confidence interval for the true slope? Negative 1.117 plus or minus. All right, we want a 95% confidence interval. So we have to find the T star for that. And so, I don't know, you probably hopefully don't need to draw a picture anymore, but I am going to. So if that's 95%, that means this is 0.025, right? 0.025, 2.5% on each tail. And so when I inverse T this, that is going to be my boundary. Distribution T inverse T. Let's see. My area is 0.025. Ooh, what are my degrees of freedom? I don't remember the sample size. How many do we test? Don't make me count. It's going to make me count. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Did it say 30 somewhere and I just missed it? All right. So our degrees of freedom will be 30 minus 2, right? 30 minus 2. So 28 degrees of freedom. 2.048 is my T star. Times, all right, and what is the standard error? So the standard error, that's the one I accidentally said was the slope before, right there. The standard error of the slope, this is the variable here for row, that is the slope, and 0.947. Type that into the calculator to see what we get for our actual interval. So negative 1.117. Let's do the minus 2.048 times 0.947. So negative 3.056. And then the same thing, negative 1.117 minus 2.048. No, plus. There we go. .822. Ooh, this one has kind of an interesting characteristic, doesn't it? Maybe we'll save that conversation for later, but do you see what's interesting about that confidence interval? Alarm bells should be going off in your head right now with that confidence interval, but maybe we'll save that for later. So I am 95% confident. The interval, I think we like putting the interval at the beginning. The interval, negative 3.056 to 0.822, contains the slope. Whoa. Slow it down. The slope of the population regression line for, all right, context. What is this regression line for? Test score described by row number. The regression line for students' test scores described by their row number. I want to make sure we have both the dependent and the independent variable described there in our sentence. All right, ladies and gentlemen, I hope that kind of makes some sense for how we do that confidence interval for the true value of a population's regression line slope.